Like Chris said, I'll be talking about the detection of swimming pool features for wildfire suppression. So this last summer, in the summer of 2013, off the southern coast of Spain, there was a wildfire on the island of Majorca, and it burned about 2,300 hectares of land. And it started in the town of Andrax and spread along the mountainsides. And as you see in the image, Andrax is almost completely surrounded by mountains. And firefighting crews use every means possible to try to contain the fires, even through the use of helicopters with water baskets. If you look at the bottom left-hand corner, you'll see all those homes along the hills. And when you zoom in, one thing you might notice is the high density of swimming pool features. And the swimming pools were actually used during this fire as a means to, as a water source to put out the fires and could try to contain it due to the proximity between the swimming pools and the actual site of the fires. So here's one example of a helicopter pulling from a pool using a suction device holding the water in its underbelly. Then more commonly, the helicopters with the water baskets that hold about 324 gallons of water. And here's a shot coming from someone's backyard with that same type of water basket. Now during this event, people were using their cell phones and taking picture shots and recording video footage of these events, and it became viral along the internet. YouTube has plenty of videos of this, and it's showing the efficiency of using these swimming pools due to the proximity of the wildfires. And so from this, I came up with my project idea. Well, what if you're able to have the location of all these swimming pools in advance? Would these firefighting aviation crews be able to efficiently plan their flight routes to attack these wildfires? And that led to this project goal, to efficiently create a database of swimming pool features to provide firefighting aviation units with a timely option to suppress wildfires. This is going to be done through the use of remote sensing and GIS technology. So a little overview I'll be getting into tonight is I'll be getting in depth about the data used, the methodology performed, the results I got, and a conclusion and how this study can go even further. So to get a brief idea of how I'm going to do this before I dig into the data, I'm going to take multispectral imagery and use it to locate a reflectance value for water. And then once I have those water bodies identified, turn them into vector-based pool objects. So there's three main factors that went into choosing my data: the availability of obtaining the data, the cost of acquiring it, and the overall general quality of the data. And these three factors also decided on where I was going to perform my study area. I originally wanted to do the study on the island of Majorca, Spain, but trying to acquire international GIS data is sometimes difficult, so I had to choose a different study area. And what better place to choose than Tucson, Arizona? So specifically, the study area will be in the northeastern extent of Tucson on a 25 square kilometer area. And although this area is not prone to wildfires, it's going to be perfect for the methodology of trying to detect the swimming pool features because there's a high density of swimming pools among these custom homes. So for this study, I'm going to use two sets of multispectral data. And the reason why I'm going to do this is because I want to compare the results I get from two different types of MSI data. So for the first one, I'm going to use the National Agriculture Imagery Program's NAIP data. It comes in 4 bands with the colors red, green, blue, and near infrared. We've seen the results we got from Landsat imagery and these other talks we've had over the week, and that's at about 30 meter spatial resolution. So if you imagine the 30 meter compared to this 1 meter spatial resolution, it's a pretty high resolution. And this data is available freely through the USGS for certain years or through a buy-up option for certain data packages. For the second set of data I'm using the Worldview 2 data. It comes in 8 bands, but for this study, I only acquired the red, green, blue, and near-infrared bands. What makes the Worldview 2 data so special is it's at a 46 centimeter spatial resolution when pan-sharpened. The only trade-off is this data is a little more expensive. It's about $16 per square kilometer for the general public, but with the help from the university, I was able to get for this study. So when viewed at the same scale, well, this is when you're zoomed in real close, so that's why it's all pixelated like that, but you can get the overall idea of the general quality of the data when you're zoomed in close. The NAIP data being 1 meter and about ½ meter for the Worldview 2. The NAIP data is going to have a larger area of mixed pixels than in the Worldview 2, and you're going to see that around the swimming pools, especially along the outlines of the swimming pools. So I brought in Pima County parcel data within the 25 square kilometer area, and that's about a total of 2,038 parcels. And what the parcel data is going to do is going to provide attributes that you can assign to the swimming pools once you have them located. Attributes like the owner's name, the mailing address, and latitude, longitude, and parcel ID information. So now that I have the multispectral data, I need to find an index that I can use to detect the water. And so what I'm going to use for this is the normalized difference water index, NDWI, not to be confused with NDVI. It's similar in the sense, but you're using the green band instead of the red band. It was originally founded by Stuart McFeeters in his 1996 paper when he found its ability to delineate water features from other types of land cover. So when you're plugging into a raster calculator, this is what it's going to look like. You're using the band 2, which is the green, and band 4 is the near infrared band, and timesing each subsection by 1.0 so you get that pixel back in a decimal format. So to get an overall idea of what you're going to get when you perform this calculation, so you're going to get an output raster, and each pixel is going to have a value from -1 to +1. And all values from 0 to +1 should represent water. So here's the NAIP data, and after I performed the NDWI calculation on it, this is what I got. It picked up the swimming pools, but it also picked up the white rooftops on that Santa Fe style architectural buildings because it's flat and the reflectance of white. And I don't know if you can see it from where you're sitting, but at the stop sign, it also picked up a car, so it's reading that metallic paint from the vehicles. For the Worldview 2 data, I was expecting to get a nice tighter group of just the swimming pools, but unfortunately that wasn't the case. It actually picked up a lot more area than the NAIP data. And so it did pick up the swimming pools, it picked up the roof, certain soil types, and the asphalt along the roads. And although I performed the same calculation between the NAIP data and the Worldview 2 data, the reason why you're going to see this is because every sensor is going to have, it's not going to have the exact same range for each band. And in this case is the near infrared band. The Worldview 2 is much shorter. So now that I have this mess in front of me, I have to find a way just to get the swimming pools and get the rest of that stuff not counting. So I need to locate a threshold. So I created 2 point feature classes, one for pool features and one for non-pool features. And these point features are going to serve as a sampling method to extract values from that NDWI raster so I can see where they're distributed among a histogram. So for the pool features, placed in the center of the pool to avoid mixed pixels, and then the other points were placed along the non-pool features. And that's going to give me a histogram. The histogram was rather lengthy, took up several screens, so I'm showing you a simplified version of what I got in response. For the pool features, the pixel values were ranging anywhere from 0 to 0.308, and for the non-pool features, luckily is in a nice, tight, small range and high frequencies ranging between 0 to 0.025. And from seeing the distribution of it being at the front end of where the pool features were, it's safe to say to put a threshold value right after the max value for those non-pool feature samples. So this is what I got once I found that perfect threshold, and this is with the Worldview 2 data. It was able to keep the geometry of the swimming pools pretty well, and it is also able to pick up like you see at the top of the screen, you see a little speck of red, and is able to pick up the water underneath the vegetation cover of that tree that was covering the pool. So I'll have this in a raster format, and then I need to turn all those red bodies into vector-based objects, into polygons. So using the Esri's tool, raster to polygon, you can now have swimming pool polygons. And then at that point, you can put centroids in the middle of every swimming pool and generate a latitude and longitude for each single swimming pool. And like I spoke of earlier, bringing in that parcel data, that's when you can start joining all that other attributes, like the owner's name, the mailing address, and the parcel ID number. So for the NAIP data, it is able to pick a total of 650 parcels containing swimming pools. And it picked up quite a bit for being 1 meter spatial resolution. For the Worldview 2 data, it picked up a total of 885 parcels containing pools. And one thing I must note is the data was not, or the imagery was not captured on the same day, so therefore there's going to be lots of places where the pools did not have water in it at the time, or the pools were filled in, or there's nothing built yet. So in order to get a better idea of how well the Worldview 2 data performed over the NAIP data, did an accuracy assessment, and the way it was classified, it was either pool parcels or parcels. If there's a pool with water present, it's counted as a pool parcel. If there wasn't any water present or any pool, then it's just parcel. Then for this, out of the 2,038 parcels, 250 of them were randomly selected for this accuracy assessment. Then using Google Earth's historical imagery tool, you could back up to that date and try to cross-verify. So for the NAIP, you got an overall accuracy of 82.4%. In the remote sensing community, you usually want to achieve an 85% for what's good and what's not. And the NAIP data just came shy of that 85% mark. For the Worldview 2 data, it was able to achieve a 93.6%. So much higher than what you're going to get with that NAIP data. Now, during the validation process, I was coming across pools that were clearly blue, but I was not being able to detect it at all. And then when I sampled the pixel values, it was registering as other NDWI values that were matching something along soil or some of the rooftops. And it had me completely stumped. But then I thought about, well, what about the presence of tarps? Because it's blue, and when you see it in the image, you're not going to be able to tell any different. And then I found this distinct example where there's two hues of blue, and only one portion of it was being detected. And I thought, well, maybe the depth of the pool, but that wouldn't be the case because still you're going to have to get that reflectance of the water. So I was stumped, and I needed to find a way if that was truly a tarp or not. So what I did could be kind of considered creepy, but I took the owner's name and I Googled him. And sure enough, I found his phone number, gave him a call, let him know I'm a graduate student and I'm doing a study in his neighborhood. If he'd be willing to answer some questions to help me with my studies. And the guy was very nice, and he said yes, he would answer questions for me. So I asked him, do you use a pool tarp in the month of April? And he says, well, why, of course, yeah, we do. We have a pool tarp, and we had it in there for the last few months. And then he said, and I asked him, well, does the pool tarp cover the full length of your swimming pool? And he says, no, it covers roughly about 3/4 of the swimming pool. And that's exactly what you see on the right there. And I asked him how many kids he had, and then he hung up. So in conclusion, mass detection of swimming pool features through multispectral imagery is possible, and it holds an advantage over manual digitization. If you're trying to digitize thousands of swimming pools with the click of a mouse, it's going to take many hours, and the labor costs will probably end up being pretty high. So using multispectral data, it is possible to do this. Then having this known location data for swimming pools, firefighting and aviation units can officially plan for their flight routes to strategically fight wildfires. For future studies, I believe meeting with the pilots that actually fly these helicopters and try to understand what safety hazards they come across when they approach these swimming pools, and like the height restrictions or anything along that lines, then use LiDAR. And then that way you can filter out which pools are actually safely accessible. And that concludes my presentation. And if you guys would like my email address for contact information, it's right there. And then I'll open up for questions. Yes, Taylor?
So you said it was a wildfire in Spain where they started using that technique of using water from swimming pools to fight wildfires. Do you have there any plans to use that technique elsewhere?
Well, I've heard of them using it in California at some locations, but I'm sure the laws are a little iffy, so it's a little easier to do internationally, but probably a while. Yes?
Does it require the permission of the owner, or did they just like do it?
I actually do not know much about the laws. In Spain, I think they just showed up. So. But with having like the attribute information of like the mailing address, and then if they were trying to push for those laws, then they could actually probably mail out something, try and get permission, or maybe I'd have to go through the FAA.